All right, class, let's begin. This is the second half of today's lecture, the beginning of the exploit development lecture series. We are not covering the following. We already did that. And yeah, before we jump into it, I want to jump to the digital attack map because since Monday, the world's largest DDoS attack has been going on. And the victims are primarily in the United States, although a lot of it is coming from the United States, but it's also coming from around the world. And the victims are primarily Europe, the United States, and poor Peru. Um, Somewhere in Peru is getting hit. And what they're exploiting is not anything related to these lectures. They are exploiting the vulnerability instead of what was done last year in the world's largest DDoS, which was DNS server amplification. They are attacking network time protocol. So if you've noticed that your system's time has changed to something inaccurate, perhaps off by an hour, or perhaps your emails since Monday have been dated weirdly, hours off, this is because botnets have been attacking the network time protocol servers that all of your computers coordinate with and do handshakes with every now and then so that everyone around the world has an agreed upon time. However, if these time protocol servers have more people talking to them, telling them that this is the time instead of Y, such as a botnet doing this maliciously, you can pull off an attack. And what it does is it's an amplification attack that they send a simple request message to request the past 60 users and that have contacted the time server. And this creates a very, very large packet or series of packets, and then they direct it towards the targets. And so the result is from this botnet is, and maybe coordination of botnets, is a massive DDoS attack, the largest the world has ever seen, which is pretty awesome to behold. But let's get to the lecture. So we're going to cover some very basics of exploitation theory. And exploitation theory is rooted in the target architecture. And for much of this semester, we're going to be focusing on Intel x86, which is based on the von Neumann architecture. And if you've covered this in your computer science classes, this diagram on the right should look very familiar. The von Neumann architecture is the most popular system model around the world for personal computers, and it is going on 45 years old and is still going strong. And one of the major features and perhaps flaws of it is that it cannot distinguish between data and instructions. As a feature, early on in the beginnings of computer science, this allowed for compilers, interpreted languages, and many of the things that we now enjoy, interpreted languages like Python, JavaScript, just-in-time compilation. It effectively treats data, performs an operation on it, and then it becomes instructions and begins executing it. This not distinguishing between data and instructions and allowing the processor to execute whatever it wants allows for these things. And back in the day, this was influenced because old punch card and tape card systems had separate memory for instructions and data, and they took forever to set up. And the ability to treat code and data as interchangeable and do whatever you want really made things more convenient, and which is why it took off initially. However, this is the same reason coming from just ending the dynamic taint analysis and taint analysis lecture. We understand that if you take user data and don't care if it becomes instructions, that's how attackers are going to get in. And that's one of the major reasons for so much hacking and malware. However, as we will see later in the semester, that if you simply fix this by switching to a different architecture, that's not going to stop hackers whatsoever. However, Some people disagree, but they can be wrong. Um, this is a fantastic read. It's an article interview from the son or grandson of Professor von Neumann, and he's calling for a change of this paradigm, how we need to move away from this model, and that this principle is really harming us, and that we can have all these conveniences on a different architecture that's more secure. Arguably more secure is the Harvard architecture, which has completely different memory for instructions and data. Um, However, in essence, say you have a 32-bit address space. This would mean that you can have arbitrarily as much memory here and arbitrarily as much memory here, and there's some sort of switch that determines what you're reading from. That switch, you only have two choices, is effectively a binary decision. So you can reasonably say that then this is just a 33-bit memory space as opposed to a 32-bit memory space, because all you have is a bit differentiating between the two. And so this is a little thing that has worked its way into a security feature. We'll explore later the NX or the DEP bit, and we'll explore how this affects exploits and mitigates many attacks. It has been a useful advancement in the realm of security. So on that note, like the slide says, most modern processors implement small parts of a modified Harvard architecture, mostly for security reasons nowadays. So there are other architectures that you are to be aware of. As the world is being controlled by more and more smart things, we're going to see more and more architectures, perhaps. And there have been efforts in trusted computing base. However, every now and then they have some success and then it all falls apart, it seems. But it's a worthwhile endeavor, and many people feel strongly that it's impossible. There's other architectures like tagged architecture, which is very similar to taint analysis, where each piece of data carries credentials and is tagged as having some metadata, maybe user input, and thus can be easily taint analysis and tracked. And there's also capability architectures, which are the opposite of access control lists, where users are specified what capabilities they have. So in this model, every software object would carry metadata and specific permissions describing what it can do on that computer. However, the problem is it has extreme scalability problems. It's not a scalable solution. So the basics of exploitation are driven really by finding the flaws in the habits of the computer industry, the IT industry, and the security industry, which are primarily driven by market forces. Every now and then you see features added into some popular application that seem to have completely forgotten the lessons that we've learned in the past. And for instance, Android's operating systems did not learn a damn thing from the past 20 years of security and operating systems, and they have non-existent permission controls, most would consider, if not just downright terrible. However, this allows for Android to do more advertising and collect more data on the users, and for third parties to collect more data, which then introduces a market driving force of how much do you value user control over a device versus how much value can be squeezed out of that device from advertisers monitoring what's going on. Interesting juxtaposition we have there. So another aspect of security is that many times in many sectors, IT professionals are limited to following checklists and have to do things according to guidelines, and may have their hands tied to do further things. And that's where, as an attacker, especially doing pen testing, you have to look um, and find those problems. Perhaps they can improve their procedures, unfortunately, if they're limited to them. So, as I said, in von Neumann architecture, due to the inability to distinguish between instructions and data, you can corrupt data with instructions and then hijack control flow because it saves the previous instruction pointer as a return address on the stack. And we're going to explore precisely how the stack operates with example and then exploit it later in this lecture. So most exploits can be generalized into a three-step process: some form of memory corruption, some form of attacking, targeting whatever stores the control flow data in the process, memory space, and hijacking that to point to malicious instructions, or perhaps pull off malicious computations, and we'll cover that later in code reuse. So, as a disclaimer, in the beginning parts of this lecture series, most of the initial techniques you're going to see will not work on modern systems because of advancements in security. And so we're just going to call these vanilla systems that don't have any countermeasures. And the textbook, Hacking the Art of Exploitation, has a CD that has a very nice vanilla system that's great for learning. Makes this stuff very easy to talk about and demonstrate. And secondly, what I talked about in the previous part of this lecture for today is that exploits have to be first and foremost developed with the target architecture in mind. Intel is Little Endian. The mnemonic tip I always give is that Intel has more characters in common with Little than Big Endian, so Intel, Little Endian. It's just the easy way to remember it. So as I talked about already, if you have AA, BB, CC, DD, and you want to store it in memory, it's going to be stored DD, CC, BB, AA, because the Little Endian goes first, and the rest follows accordingly. Is actually quite common for processors to be Big Endian. Some processors can be bi-endian, like ARM processors, and you'll see this in CTFs where they intentionally flip back and forth between the endianness just to make it as frustrating as possible. And so we're going to start off with buffer overflow. It's really simple. And to recap some of the definitions that we need to know. To exploit something as a verb is to take advantage of a vulnerability, basically to gain access, or in other words, so that the target system reacts in a manner other than intended. Usually the goal is to gain access. By gaining access, you can compromise all the three aspects of security, which are confidentiality, integrity, and availability. If you already have access to something, you've already compromised the confidentiality, perhaps, and you can have perhaps permissions to compromise the integrity, and you might be able to just bring down the whole service too, and compromise the availability of it. An exploit, as a noun, is essentially a set of instructions or a tool or code that is used to take advantage of a vulnerability or to pull off an exploit. Very commonly, it's synonymous with POC, proof of concept. You'll often see proof of concepts demonstrate a vulnerability by, instead of popping a shell, it'll pop up calculator. That's very common proof of concept. So a 0 day, as we know, is an exploit for a vulnerability that has not been publicly disclosed. It's privately known to a few. Sometimes it is used to refer to the vulnerability itself or the bug itself. Sometimes it's used improperly to describe a bug that may not be a vulnerability as well. Shellcode is a set of instructions that is to be injected and then executed by an exploited program in an exploit. It is often the payload itself, if not an intermediate payload, or stage 1, stage 2 payload. We'll cover those. So say you've done some fuzzing, or you've done some source analysis, or you've done some reverse engineering, and you've discovered a vulnerability. You have to then think about what type of attacks make sense. Is it an overflow on the stack? Is it an overflow on the heap? What sort of countermeasures might be in play? Are you able to insert code? How much space do you have to insert stuff? Can we redirect execution? And so let's explore this with buffer overflows. It's quite simple. We've already covered a buffer overflow on heap and showed how it's not that difficult to understand. And as I said earlier, overflows happen when you put too much stuff in too small of a space. That was basically the answer on the exam. Anything related to that was accepted. As for the grading, homeworks 1 through 3 will all be posted on Blackboard, as well as the exam on Blackboard this weekend. So you have time to decide before drop day next Friday. And homework 4 will be extended to Monday, and I'll send out an email about that. So we also covered this earlier, that the process memory layout for Linux has various segments. There's the stack, the heap, the .text segment, the .bss, the .data segment, and they hold the corresponding things that we've already covered. Most of the user input goes into the stack or the heap. Stack is for local variables, environment variables, passed arguments, the saved instruction pointer for returning. Heap is for dynamically allocated variables and dynamic space. So let's look at the following code. We're going to step through an example. So this is using the stack. High memory is here at the bottom. Low memory is at the top, and the stack grows towards lower memory. But it's important to remember that, important to know that memory writes, no matter where they happen, write towards higher memory. So any form of writing for a buffer would write down towards higher memory in this. So let's start from the very beginning. We have this main function, and we're going to walk through how this is constructed and how we got to this point where EIP gets to the return off flag in this other function. So at the main function here, we're going to have main stack frame, and the stack pointer is going to be pointing at the top of the stack frame, the top meaning the lowermost memory. And eventually the processor is going to get to this line of code, or the code supporting this, to call function and provide an argument. And the first thing it's going to push is from right to left is going to be the function's argument. So it's going to be a pointer to buff. Then it's going to push the return address so that when it returns, it comes back to evaluating the return value from function in this if statement. And then it's going to push the stack, the save frame pointer, so that when it's restored, ESP will point back to this region of the stack here. So the main's stack frame is restored. This is the prologue. This is the activity on the stack from the prologue of effectively the function. And when we jump into the function, EIP will roughly point to this line of source code. So var1 is going to get put on the stack and it's going to be set to 0. And then for this 4-character buffer, it's going to allocate it here on the stack. And say we have some code, and if, say in this code, there was a buffer overflow vulnerability, say it's just a stir copy, and we write more than 4 characters, it would write in this manner, and say in the 5th character, it would overwrite var1 on the stack, and it would write towards higher memory accordingly. Now, it's easy to see that if you keep going, you're able to overflow the return address on the stack. And that's an important target for attackers. So this is out of place. So here's just a toy example. We're going to take these two code segments, and we want to know in which one is auth flag exploitable by Stack Overflow. So in each one, it declares auth flag, declares the password buffer, does a vertical stir copy, and then it returns the auth flag. How can we get it to return whatever we want for the auth flag? And we're not talking about putting shellcode in here. We just want to overflow auth flag just by one byte and set it to whatever we want. So in order to reason about this, we're going to have to build the stack. So you have to remember which way it grows, think about what gets pushed on first, and the order in which memory writes. You should pause at this point and take out a piece of paper and try and do it if you can't visualize it in your head. So I guess terminology is worth covering is that this may be an execution control point. It may not be the return address, but it does influence the control flow of the program. So hence it's called an execution control point. Perhaps it's used to in an if statement and then decides a branch or a series of branches. So the stacks respectively for these is that the low memory is here. On the buffer overflow, this one on the right is going to write towards higher memory and is not going to write towards the auth flag. The one on the left is going to write towards the auth flag because auth flag happens to be before it on the stack. So one way to remember this when auditing source code is that in the absence of reordering and function level countermeasures that scramble the order of instructions, source code overflows. The overflows typically write upwards in source code. That's what I'm trying to say. So we'll cover some countermeasures later that break this trend. So stack is the last in, first out structure. It's pretty simple. If you've taken a computer science course before and data structures or computer organization, you should have covered it. It's very simple. So as we've covered before, that when a function calls another function, it pushes the function's arguments on the stack, however many there may be. Then it pushes the return address, then it pushes the save frame pointer, so when it returns, restores the stack frame, and then the local variables get pushed on afterwards. So if you can alter the return address for any given stack frame, you can cause the processor to point to other parts of memory and start executing there. So we've covered how heap overflows allow you to arbitrarily write a pointer, or at least part of a pointer in practice, and other arbitrary writes are off by 1 errors that write perhaps 1 byte more than a buffer allows, and integer errors that influence the writing perhaps of a character to an array or string, perhaps allow you to write prior to the array or past the array. All of these sorts of vulnerabilities, when in practice and combined with each other, can allow you to hijack the return address on the stack and thus hijack execution. So, yeah, I covered this. This is pushed prior to jumping to the function, and this is part of the prologue. Let's do a very simple demo, and that'll be it for today's lecture, with the Art of Exploitation live CD. I have a demo set up, and this is the command history. What I did is I took the auth overflow 2 example provided by the book, compiled it. I did the following just to make it so that when I pop a shell, it's popped under a different user. The only reason I did that is to make it easier to demonstrate. I can see that, oh, hey, I've popped a shell under a different user, as opposed to, oh, hey, it crashed and didn't work, and this isn't a different shell than the one I ran the command with originally. So that being said, set the SUID bit and have it running as root. And what we have is some shellcode that, when you write it, is basically assembly instructions for the given architecture. And we're going to cover this in the next lecture, so don't pay attention to this too much. And what we've done is we've compiled it into a file. And when we look at that, it's just gibberish. That's because it's compiled into machine code. And what we do is I've put this into an environment variable. So as I've done cat shellcode.bin, it basically prints it out as a string. What this following code lets me do at the bash prompt is put a payload and a not sled into an environment variable. And environment variables are located on a stack of every single process. So if I spawn a process or application with this shell, it will load the shell's environment variables. Your environment variables are usually set by init when it spawns the first process, and the rest of the services spawned after that and applications spawned after that inherit those environment variables for that user. Well, this is just a toy example. Assumes you already have local control in the system. So I'm just demonstrating how a buffer overflow could do a privilege escalation. So by doing this, I set this environment variable. So if I echo it, I'm going to get a bunch of gibberish, and you'll see maybe some strings like X, Q, H, S, H, H, bin. And it's not going to make a whole lot of sense. And that's fine for now. Let me refresh my memory. So what we want to do is, for this code example that we have here, we're going to target this exact code example on pop shell and privilege escalate. And so when we run auth overflow, it's going to tell us access denied. We're going to have to give it the right password or secret. It's probably a string in the binary itself. Brillig or outgrab, because this is just a simple example. There we go. Access has been granted. So that would be like a 1-point CTF problem, just solving that. Strings is very helpful in CTF. It should be one of the first things you run on a file, let alone from the command file, which shows you a lot of information about a given binary. It tells you that this is a 32-bit executable. is compiled for Intel 8386. In other words, i386. This is the version of system calls it's using. This is the kernel it's been compiled for. And it is dynamically linked. In other words, it is used in shared libraries. And it is not stripped. Not stripped is something we'll cover a little later when we get more into debugging things. So, there's also readelf that will tell us more about a binary. It'll give you a ton of stuff about the binary, perhaps even the compiler that was compiled with. That all aside, what we're going to do is we are going to explore a buffer overflow with this. So instead of just typing a ton of characters, I'm going to bash escape and give it a Python generated string and see what happens. Whoops. This is all wrong. Python-sc print a 200. Let's go into segfault. So there's a buffer overflow, and the way to determine where it is would be to pass it a pattern, and we'll do that in an example next time. But we know this buffer overflow. I don't have to be precise at all, and I'm going to demonstrate the very basics of an exploit here. So what we want to do is point EIP to the shellcode that we stored on the stack in the environment variable. So this nice little function, file get, is a application provided by the book that if you give it a program, an environment variable, it'll tell you exactly where in the process space that is located. So for shellcode, we want to know where it is for auth overflow 2. And so it's going to tell us that it's going to be at OXBFFF9OE. So what we can do is auth overflow 2, instead of giving it precise number of garbage and then putting in this address, what we're going to do is just put in this address and just repeat it until it works. So little endian address is going to be OE F9 FF BF. And these /x's are basically a C-level string escape. So that it interprets as not as characters, but as a byte. So this is, instead of going to be 8 characters, it's going to be 4 bytes. And what I'm going to do is I'm going to just repeat it a ton and smash the stack. And I need to actually give it a valid Python statement. Print. Can't type today. And what I've got is a shell. You'll see this a root shell because I've set it just to make it easy to demonstrate. So that is exploit 101, as simple as it possibly can get, and it's never that simple. That's just to demonstrate the concepts. So that's where we're going to end the lecture for today. And we're going to pick up next time with return to libc style techniques.